everybody. For this lecture, we are going to talk about paleoclimate or ancient climates and global warming today, modern global warming. Okay, so the Earth is constantly changing. So we all know that. It's a dynamic Earth, meaning it's ever changing. And with its changes, there's a lot of cycles that we have on this planet. So one question that is more of a relevant question between scientists and politicians and whoever else is climate change, and this idea of, is climate change happening, and is it a natural geologic process or is it man-made? And so that's a very relevant question to today, and it's what people still argue to this day, although hopefully by the end of this you can see that man-made or anthropogenic climate change is extremely real, and it is happening. And although Earth is a dynamic planet, meaning that it changes through time, and that there are natural events that can cause climate change, and they have through the history of Earth. If you look at climate change and our impact it has on the planet, it's unquestionable that humans have played their part in changing Earth's climate. Okay, so let's go through some of these changes and cycles that the Earth has experienced. Okay, so we all know that the Earth is made up of tectonic plates, right? And that these tectonic plates, over time, they smash into each other, they separate into each other, they form supercontinents, et cetera, and et cetera. So these tectonic plates are shifting around and changing constantly through the Earth, right? And so that's one of the cycles that we have on this planet, right? But there are many other cycles that contribute to this dynamic planet, right? And life on Earth is due to the interaction between these different cycles, between the lithosphere, which is where we have all of our rocks, where humans live, and the atmosphere and the hydrosphere. So the atmosphere is what envelopes our planet in a nice blanket. Okay, in the hydrosphere, that's where all of our water is located, right? So the lithosphere, atmosphere, and hydrosphere. Okay, these three spheres on Earth are all in relation with one another, and they all talk to one another. So when one is not feeling well, the others know about it. Okay, so what are the different types of change that we have on Earth? We have gradual and we have catastrophic, right? So gradual you can think of in terms of plate tectonics, so extremely small, right? A plate will separate gradually from another plate over time. Whereas catastrophic, you can think of, let's say, a meteorite impact. That's something that happens instantaneously, and it's catastrophic. Frequency, unidirectional versus cyclic. Okay, so one direction or a cyclic circular motion, that's frequency. And agency, so who's causing it? Is it the Earth or is it man? So geogenic or anthropogenic. So anthropogenic is a term coined for the period of Earth that has been influenced by mankind. Okay, so a couple of these cycles, again, the supercontinent cycle, this is something that happens over millions and billions of years. So we have plates colliding and separating from each other on and on, over and over and over again. We are currently not in a supercontinent as of right now, but in millions of years, we probably will be again. The Wilson cycle is a part of that supercontinent cycle, and this is the maturity of ocean basins, right? So this is also a cycle. The rock cycle, I hope we all know the rock cycle, right? We have three different types of rock, and these can form into another type of rock, right? So igneous can become sedimentary or metamorphic, which can turn into an igneous, et cetera, et cetera. The hydrologic cycle are motions between different bodies of water. Okay, so you have oceans, surface water, groundwater, ice caps, glaciers, These are all different types of water reservoirs that are in relation with each other. You have the sea level cycle, which is actually geologically pretty unstable, and it's gone up and down many times in Earth's history. And we know this because of our friends, the sedimentary rocks that preserve these sea level changes. Okay, so sea level is something that's not super stable on Earth, and that is something that rises and falls throughout geologic time. So you can see, at least in the past 500 million years, the rise and fall of sea level. So today, right at the edge of the Cenozoic, you can see where sea level is at 0 meters. That's our sea level of today. But in the past, the sea level has been different. Okay, and another important one is the carbon cycle. And this is a cycle between the different carbon reservoirs that we have on Earth. So carbon, so we have a lot of carbon dioxide that's being released and absorbed on our planet. And so this is the big one. This is what is going to come into play when we are talking about climate change, right? So the addition of carbon dioxide and some other gases into the atmosphere, specifically methane, but there's others, is really the culprit behind climate change, right? It's what's causing a warming in our atmosphere. But carbon dioxide is something that's very natural on our planet Earth, right? And there are processes on Earth that release carbon dioxide naturally. And one of the big ones are our volcanoes. Right, so volcanoes emit gases, and one of them being carbon dioxide. And so volcanoes are a naturally occurring thing on Earth that release carbon dioxide, right? And to balance this carbon cycle where we have the release of carbon dioxide, we actually have things in our Earth that hold on to carbon dioxide, specifically our rocks. So our limestones, and our other types of sedimentary rock, they trap the carbon. So when those rocks are weathered, or released, or let's say you have a sedimentary rock such as coal that is also having a bunch of carbon dioxide absorbed into it, when you take that material and you burn it or you break it apart, you're releasing all of that carbon back into the atmosphere. So when you destroy these types of sinks or these types of reservoirs that hold on to the carbon dioxide, you're releasing some of that right back into the atmosphere, right? So destroying these sinks is actually releasing a bunch of carbon dioxide. So we have our natural processes such as volcanoes emitting carbon dioxide. When we talk about man-made global warming, that's really taking these reservoirs that hold on to the carbon dioxide. So all of our fossil fuels or coals or organic rocks, and we are destroying them and releasing them back into the atmosphere. Okay, so this is the carbon cycle, and it is looking at what types of processes release carbon dioxide and which types of reservoirs hold on to carbon dioxide, and so why these are important to protect or at least limit our use of destroying these different sinks. Okay, so this is a very complicated but encompassing carbon dioxide carbon cycle diagram. So I'll let you all go through that yourselves. And again, carbon is removed from the cycle for long periods of time when they are stored in limestones, fossil fuels, shales, or other types of rocks with fossil fuels. This carbon is also stored in organic matter such as trees and animals, and it's returned to the atmosphere by burning all of this organic matter that has the carbon within it. This can also happen naturally through the metamorphism of carbonate rocks and the degassing from oceans. Okay, just a couple more slides on the carbon cycle. If you didn't understand the last couple, these are just to re-emphasize what that means and what it looks like. Okay, so we talked about volcanoes emitting carbon dioxide into the atmosphere. So one thing that we have to consider when we think about climate change, either ancient or current climate change, is this idea of how much carbon dioxide do volcanoes emit into the atmosphere. And if you're changing the rate of volcanic activity, so most of our volcanic activity are really along these divergent boundaries where you see this constant emission of carbon dioxide, right? A lot of it is underwater, but there are some on land too, right? And so this divergence is going to cause all of these flood basalts, and they're going to cause this really widespread volcanic activity. Again, it's not going to be as explosive as, say, a convergent boundary, but there's going to be more a widespread area affected by this divergence, right? Well, if you speed up that divergence and you speed up, let's say the Mid-Atlantic Ridge is diverging very slowly, if you speed that up and you increase volcanic activity, that is going to affect the feedback loop between the carbon cycle. So you can see fast seafloor spreading inputs rapid carbon dioxide, which warms the planet through greenhouse gas climates. You get increased chemical weathering, which removes more CO2 through destroying or disintegrating those carbon dioxide sinks like our sedimentary rocks, and then you get reduced warming. So you have this fast seafloor spreading feedback loop. Whereas if you have a slow seafloor spreading, you get slow CO2 input, you get a cold icehouse climate, and then you get this feedback loop like so, but just complete opposite. And so these feedback loops take tens of millions of years to happen. Okay, but that's one example of how these natural geologic processes can influence the climate, right? But they're on very, very slow time scales. Okay, so again, these long-term climate changes operates on millions of years. Short-term climate change is on the order of 10 to hundreds of thousands of years. Okay, so our most recent climate, so all of human history, could be considered short-term climate change, right, as opposed to long-term climate. Okay, so the role of greenhouse gases in climate. Okay, so this is a good spot for me. Okay, so without greenhouse gases, Earth would be a dead, frozen world. Okay, so water, H2O, is the most important greenhouse gas, followed by carbon dioxide. Okay, there's other greenhouse gases, but these are the two most prominent gases in the greenhouse gases. Okay, and so greenhouse gases, they work in the same way as a greenhouse does, right? So a greenhouse is a little glass house that you put around your favorite plants, and it traps in the heat, okay? This is what's happening to our planet. So you have our atmosphere, which does have some water and CO2 in it, but if you increase these gases, it creates a warming of the planet, which gives a positive feedback cycle leading to more and more and more warming of the planet. Okay, and here's a GIF of the greenhouse effect. Okay, some is absorbed by heat. Most of the heat is absorbed by these greenhouse gases and reflected, warming the Earth. Okay, and then it goes on and on. Sunlight reaches the Earth. Some energy is reflected. Some is absorbed. Okay, and this is how you start to get these greenhouse gases. Okay, so it builds up over time. Okay, so we have our composition of the Earth's atmosphere. So in our previous lecture, we looked at what is in our Earth's atmosphere. And only a small percentage are these other gases. So this is where we get our carbon dioxide and our methane, our fluorinated gases, our ozone. a very, very small percentage of Earth's atmosphere, right? And so you can see these are the greenhouse gases in the atmosphere, so our water vapor, our CO2 and other. And these are our man-made greenhouse gases, right? So you can see um, basically all carbon dioxide, a large bit of methane, nitrous oxide, and some fluorinated gases, right? So you can see the natural greenhouse gases in our atmosphere versus our man-made greenhouse gases. It's basically predominantly carbon dioxide, which is caused by the burning of fossil fuels. Okay, so here's another greenhouse effect. Okay, and so this is important. Why? Because the habitability, that's a tough one, of our planet depends on our very delicate balance of our atmosphere. Okay, so we have about 0.3% of CO2 in our atmosphere, producing an average temperature of 15 degrees Celsius, right? And this atmosphere is our envelope, it's our blanket around our Earth, right? And if this balance is disrupted with emissions of too many carbon dioxide gases or methanes and other greenhouse gases, our envelope, our atmosphere is disrupted, right? So it's no longer as protected and squishy and comfortable as it would like to be, right? And so we all know that when a planet doesn't have a nice atmosphere, such as Mars or Venus, these conditions are not suitable for life. Okay, so here is a global mean temperature of climate through geologic time from 500 million years ago to present. And you can see these large swings throughout time. So the large swings of temperature through time. Okay, so it takes a long time for our Earth to stabilize and balance into this nice temperature that we see here. And that has effects from our atmosphere and the stabilization of the oxygen in our atmosphere relating to our temperature of our atmosphere. Okay, and so how do we study climate change? What are the ways that we know how climate has changed in the past? Okay, so one of the most obvious ways we can look at climate change is through sedimentary rocks. Okay, so we talked about the environments of different sedimentary rocks. So what types of temperature does coal like to form in, right? So if you find coal somewhere, you can expect that at once upon a time that region was pretty moist, it was pretty warm for coal to form, right? Because it likes these warm lagoon types of swampy areas. Whereas if you find rocks with glacial till, you can expect a cold continental setting. Okay, so looking at the different types of sedimentary rocks in the rock record can clue us into the different changes of climate that have happened since the beginning of the Earth. But if we look closer at these different rocks, we can also look at different pollens within the sedimentary rocks. So you can look at these little microscopic pollen in the sedimentary rocks when you core in through the earth, and you can look at the changing vegetation through time. So what has tree pollen versus grass pollen? So what is a colder climate versus which is a warmer climate? Okay, measuring oxygen isotopes. So this is one of the most popular ways that we can look at paleoclimate today. And this is done by looking at ice cores and by deep ocean sediment cores. And it's looking at the isotope, the oxygen isotope ratios found in the ice and sediment cores. So these are done with these really sophisticated machines looking at the bubbles trapped in ice cores or the different types of oxygen that are in the sediment cores from the deep ocean. So I don't know if I have a picture of some ice cores. Okay, here we go. So if you look at this ice core here, you'll see some layers, right? These layers directly correspond to the thicknesses of the ice and how much snow and ice accumulated in a particular year. But if you also look closely, you can see these little tiny bubbles that are trapped in the ice. And these bubbles are actually time capsules of what the atmosphere was like during the accumulation of that sediment and ice during the formation of this core. So this little bubble can be greatly different from this little bubble on top, right? Because this bubble is capturing the atmosphere at a certain point in time, whereas this bubble is going to capture the atmosphere at a younger point in time in Earth's history, right? So these little bubbles completely encapsulate the atmosphere at that point when that snow and ice was forming in this ice, right? So if you release these bubbles, you release the gas, and when you can measure these different oxygen isotopes in the bubbles, you can get the type of atmosphere that was happening at that point. And so these ice cores and also sediment cores are something that's super popular with climatologists today. You can also do it with growth rings. So tree trunks have growth rings around them and historical records. Okay, so long-term climate change. Geologists have reconstructed the global climate change, and you can see the different oscillation between the Archean all the way through the Quaternary, right? And you see these different swings between ice house and greenhouse gases, greenhouse climate. So the blues represent when the Earth was in the middle of an ice house versus greenhouse. So really globally cold climates versus globally warm climates. Okay, so we looked at that already. Okay, so what is causing, the change in these global climates? So one thing that is can impact these global climate changes are these ocean circulations. So again, plates collide and then diverge with one another, right? So as you're reorienting the continents and the land masses, you're also messing up and changing the ocean circulations. So the oceans circulate around our continents, right? And so when you're reorganizing the continents through plate tectonics, you're also reorganizing the ocean circulation patterns. Okay, and so these ocean circulation patterns are really important in controlling the types of climates that we have, because we have our warm surface ocean circulation patterns forming pretty much over the equator, and as those warm currents cool and sink towards the polar caps, right, they dictate our cold deep sea circulation currents. Okay, so when we have plate tectonics and we're reorganizing these land masses, they also disturb our ocean circulation. Okay, and plate tectonics not only does that with ocean patterns, they also does it with uplifted land area. Okay, so volcanic eruptions, again, this is a big one that can disrupt global climate. And again, this is with the release of carbon dioxide, and this traps heat and produces global warming. So abundant volcanism associated with the rifting of Pangaea may have contributed to the Cretaceous greenhouse. So when Pangaea separated, there was a ton of volcanic activity associated with that. And we all know that from our lava flows that we can see in the Northeast, such as Springfield in Massachusetts. There was a ton of volcanic activity at that time when Pangaea diverged and separated. So this caused a ton of CO2 to be released into the atmosphere, and that could have contributed to a warming of the planet because of the increase in carbon dioxide from these really widespread volcanic events. Okay, coal and oil formation. These are natural sedimentary deposits, and our CO2, our carbon dioxide, is stored in coal and organic sedimentary deposits. So we get our coal, our oil, our natural gas, all from these sedimentary rocks. And removal of large amounts of organic carbon during the coal forming area coincided with a pronounced global cooling. So when you were forming these sedimentary rocks, so when the earth was producing more of these carbon sinks. So these are the reservoirs which hold on to the carbon. When Earth was producing all of this coal and oil, it was removing a lot of the CO2 from the atmosphere. So this is related to a global cooling event. Okay, and then life evolution. So lichens also decreased atmospheric CO2, leading to icehouse conditions. Okay, so we also have, these are long-term global cooling or warming events. We also have some natural short-term climate change. So in the Pleistocene, we have actually had, so the Pleistocene is from 0 to about 1.5, a little bit more million years ago. And you can see that it's dominated by these glacial events. Okay, so there were actually dozens of glacial events that have happened in the Pleistocene. So that means the formation of these glacial areas and the melting of glacial regions. And this happens over and over and over again through millions of years. So during the Pleistocene, there were several distinct ice sheets. In several places, neighboring sheets came into contact. So you can see this diagram of the United States, and this is the extent of where these glaciers were. So much of Canada, it swings in through the Great Lake region and then swings down east to Connecticut, Massachusetts, New York, etc. So in this region here, we had the retreat of this huge glacier, right? So Long Island, parts of Connecticut, and in coastal Massachusetts was actually the remnants of this glacial event where this glacier receded and left a bunch of glacial sediment in its path. So you'll see a lot of glacial sediment in these coastal regions here where the glacier melted in from the Pleistocene. Okay, and here's some ice sheets that were present during the Pleistocene. Okay, I'm going to go a little bit quicker. Okay, so our oxygen isotope ratios from marine sediments define 20 to 30 Pleistocene glaciations. Okay, so again, our climatologists that look at these oxygen isotopes are able to measure the atmosphere through these marine sediments, right? So they are able to figure out when these glacial events happened and how far apart they were. Okay, so again, these are just parts of the geologic timescale and the temperatures. Okay, so will there be another glacial advance, right? So there's this long cycle of glacial events followed by warming events, right? So what are we in right now? So currently we're in an interglacial period, meaning that at some point in time, we are due pretty much very soon for another glacial event, right? So interglacials last around 10,000 years, and it has been 11,000 years since the last one. A cool period, a little ice age in Europe happened in around 1300, but we've basically had a warming climate in the past 11,000 years. So are we due for another glacial event? It doesn't look like it, but it is likely that we will eventually get a glacial climate, another icehouse climate. Okay. Whoops. Okay, so sea level changes. So one thing I want to point out about this is that sea level changes in glacial events matter when you're talking about land glaciers specifically. So we do have sea ice, right? But when we talk about sea level changes, we're really talking about land ice melting, okay? Because if you think about it, sea ice is already in the ocean, right? So it's already displacing a certain amount of water because of the weight of that glacier or iceberg or sea ice that's floating in the water. So when you melt the sea ice, you're not really displacing any new water because you already have that weight already in the ocean. But when we're talking about land ice, we're talking about the glaciers that are on land. So again, this huge part of the country in the Pleistocene that had this glacier sitting right on top of the land, that glacier melted. And when that land glacier melted, all of that water that was on land is now in the water. So when we talk about sea level changes, we're really focused on the water that is melting that was once upon a time on land. Okay, so sea ice is very important too. Many other things specifically are biodiversity or polar animals. But when we talk about land ice, that's what is really dictating sea level rise. Okay, so here's a diagram on that. Okay, and so the Milankovitch cycles. So the Milankovitch cycles are this idea that the climate changes every 41,000 years because of the different orbit, tilt, and rotation of the Earth, which changes every thousands of years. Okay, so I actually like this diagram better. Here we go. So the eccentricity of the Earth is the type of orbit shape, right? So the difference between this kind of elliptical or oblong shape versus a more circular shape. So when we have the Earth in this oblong elliptical shape, we have more of these global cooling events. When Earth is in this kind of circular orbit shape, it's more leaning towards a warming climate. So this changes every 100,000 to 400,000 years. Okay, the tilt of the Earth changes about 3 degrees every 41,000 years, right? And so the tilt of the Earth, depending on if it's a shallower tilt or a steeper tilt, is going to influence the climate as well. And then the precession is the kind of wobble that the Earth experiences every 19 to 24,000 years. And so these three different events that the Earth experiences, these cycles that the Earth experiences, when they are combined with one another, they will influence climate every 41,000 years or so, meaning that we will get ice ages basically on a cyclical pattern based on these three things that happen between the orbit, the tilt, and the precession of the Earth every several thousand years or so. So this idea is that these glaciers and these cooling events happen on a kind of cyclical pattern, right, depending on basically the orbit and the tilt. Okay, so I'm going to keep going. So the Holocene is our most recent point in Earth, right? And so this is where humans come into play. And if you notice on this, we also have a changing temperature. So about 0 to 18,000 years when we are in the Holocene, we had some climate change. Okay, so what causes these short-term climate changes? Okay, so we can get solar fluxes. Okay, so these are sunspots or magnetic storms that slow convection at the Earth's surface. Okay, so this can impact our shorter-term climate change in the Holocene. We can have volcanic emissions. So again, in 1815, we had Mount Tambora erupt, and that became the year without summer because it inputted all of this volcanic ash, gases, etc., into the atmosphere, and it basically blocked sunlight. So there was snow in June during that eruption event. Ocean currents can be disrupted. And this happens particularly more when we have a warming climate. So melting sea ice could alter the density of currents, disrupting the ocean circulation currents that we have. Greenhouse gases, so the sudden addition or removal of greenhouse gases changes the climate on a shorter term time scale. So this can be changes in the amounts of photosynthesizers, deforestation, etc., or the sudden release of methane from ice that is stored in permafrost, or at the bottom of ocean sediments. Catastrophic changes can impact our climate on a short time scale, but we also have humans that are also changing our climate on these short-term time scales. Okay, and so what are humans doing to the earth? Landscape modifications, so excavation, agriculture, construction, which modifies ecosystems. Organisms are not able to adapt. They destabilize established ecologic balances. So rainforest decline is largely because of human activity. You have smog, which introduces smoke and fog into the atmosphere. Pollution, we all know about pollution and contamination. Water contamination, so water is a vital source of life, which we'll talk about next lecture, and that is getting disrupted. Acidification, so acid rain is increasing in large parts of the world because of sulfate-rich aerosols from coal-fired power plants, and this changes the pH of rainfall. So we have a lot of acid rain in the northeast region, more located in Pennsylvania region because of these coal plants. Okay, and so we are transitioning away from coal-fired plants, but the effects of coal plants are this acid rain that has basically been caused by the burning of coal. Radioactive materials, these are from nuclear weapons, etc., mining and processing, ozone depletion, and then recent global warming. So this is when humans come into play. So these are some charts directly monitoring CO2. And so Mauna Loa is a volcano that I hope all of you know by this point. It's a huge shield volcano in Hawaii. And as we all know from this lecture now, volcanoes emit a bunch of CO2. So in the 1960s, they put a CO2 monitor right at Mauna Loa to monitor the CO2 emissions in a region of the world that was most impacted by natural CO2 emissions, to see the different rates of these emissions through time. And you can see that when they started monitoring directly, you can see a huge spike from the 1960s through 2010. Right? And before that, it was pretty slowly increasing, but then it pretty much skyrocketed in the 1950s and a little bit previously. And that is because of these human man-made fossil fuel burning, right? Emitting all this CO2 into the atmosphere. Okay, so here are some more charts on recent global warming and the CO2 emissions through time, right? And you can see that in the past 800,000 years, there were some oscillating patterns, but pretty recently, it's just skyrocketed the amount of CO2 that's emitted into the atmosphere. So there's really no question about it that humans are emitting this catastrophic amount of CO2 into the atmosphere. And while there are oscillations and changes through time, there aren't quite as many emissions of CO2 naturally as there are anthropogenically. Okay, and so recent global warming, whoops, come back, mostly are causing a huge melt in our polar ice caps, right? So all of our land glaciers in the Arctic and Antarctic are melting. So I have this audio clip that you can listen to talking about recent global warming and the melting of ice sheets. So we'll play that. Okay, so here's some more charts looking at the melt. So I won't go into these because you can look at these charts yourselves. You don't need me to talk to you about them because they're pretty self-explanatory. You can just look at the different levels of CO2 and temperature that are increasing in recent global warming. Okay, so again, the greatest impact to this global warming is going to be in the Arctic. Okay, so this is the 2070 to 2100 prediction of global warming temperature increase. And you can see the Arctic is extremely warm. Okay, and that parts of Illinois are going to feel like Texas in hopefully not in our lifetime, but you never know. Okay, so global warming is predicted to cause a rise in sea level due to water added from melting glaciers. Now, again, these are land glaciers specifically, ice shelves, and ice caps. The warming of the water will actually cause water to expand. So, again, warm water likes to expand, causing a greater tidal surge and tidals. Ebbs and flows in coastal areas because the water is expanded because it's warmer. Okay, and some other pictures. Future of the Earth. What is the future of the Earth? It is unknown, but we are causing some serious stuff in the world today. So who knows if we're going to see this new supercontinent that will form in 250 million years. And then the fate of the Earth. Billions of years, Earth will be vaporized. Hopefully, we're not here to see that, at least. As the sun runs out of hydrogen, it will collapse inward, causing the sun to collapse, and the Earth will vaporize with the sun. So that is not a fun future, but that is the ultimate fate of Earth. I will leave you with that. Grim diagnosis. More on climate change for the next lecture.